Okay. So I have started doing that. Okay. So perhaps a good time. The main text for this is a book by Stephen Struggers. He's an authority in this area. So he has a book on nonlinear dynamics and chaos with applications to physics, biology, chemistry, and engineering. So the material will primarily be taken from here. There are just a few things in the introduction where I add some things from different places, but mostly from the book by Struggers. Hesh has a very good, Hesh, Smil, and Divani. They have a very good book on differential equations, dynamical systems, and an introduction. So you can look at that as well. And the book by Ben Schroers. So this is in the Ames library actually. So he wrote a book on ordinary differential equations. In the second or third part of the course, you would find information on phase plane, phase portraits. Those things you can find in his book, okay? Or if you're already familiar with his book. So he used to teach at Ames for, I think, several years. So he has a book on that. So, but for the most part, it's a book by Struggers that we would use. Okay. Of course, I understand this is basically you would have a feel of what this is in a few minutes or in an hour or so, and then you can decide whether this is of interest to you. Okay. So that is by way of introduction, basically. And of course, today will be introductory, and then from tomorrow or so, or Friday, we would start with something concrete. Okay. Maybe I'll pause and ask for any questions on this. The outline, the topic, what we're going to cover. If you have any quick comment or question before I actually delve into a few things on introduction to dynamical systems. So feel free, any question? I see something on the chat here. Oh, record, okay. I just saw that, I've started recording, okay. So you can raise your hand if you have a quick question or I move on. No? Okay. So let me bring up my slides here. Hopefully you guys can see. Okay. Right. Let's do this. Okay. Yeah. Okay. So this is some information about myself. Of course, since this is recorded and you have access to it, you have this information about myself. So as I said, I'll give a historical background and then some introduction and motivation, basically on differential equations and some applications in biology. So consider that to be introductory, and a motivation for dynamical systems. So I mentioned already that the subject deals with change. We'll look mostly about change in time with systems, of course, that evolve with time. We'll probably want to know whether the system is going to settle down to equilibrium or is going to go periodically and repeat, or is going to do something crazy or complicated. That is basically about dynamical systems. So whatever it is usually the dynamics that is used to analyze the behavior. The dynamics here talks about all the machinery, the mathematical techniques, methods that we know of in tackling such problems. So dynamical ideas, they appear in various places, most especially in differential equations, classical mechanics, chemical kinetics, and population biology. Okay, so there you would see very soon that, in fact, the history is that this thing is from physics, mostly from classical mechanics, and then it's being used now in various fields, especially in, of course, chaos, and especially mathematical biology. They apply the techniques of dynamical systems heavily in that area now. Okay, so this was originally physics dominated field due to the work of Newton on differential equations in the 1600s. We all know he discovered the laws of motion as well as universal gravitation, and then he used that to explain Kepler's laws of planetary motion. Okay, so that was the work of Newton, and he actually solved what is called the two-body problem, looking at how you actually solve the problem of planets moving in their orbits around each other. So you take two planets, and then he did that using the inverse square law of gravitational attraction, right? So that was the work of Newton. So after solving the two-body problem, this is supposed to be this, but it doesn't. I don't think it works. This is supposed to be the work of Newton on the two-body problem, but after this, mathematicians, physicists tried to extend the ideas of Newton to look at a three-body problem. In this case, you can think of, let's say, the sun, the earth, and the moon, and these are revolving and around each other. How do you solve that problem? And for many years, that was a challenge, a big challenge. It couldn't be solved for many years. Then in the 1800s, Poincaré came around, and then he said that, well, maybe we should reconfigure our thinking. We should start thinking about the problem differently. So he brought a new point of view that sort of emphasizes qualitative nature of things as opposed to quantitative questions. So instead of asking where is a planet at each particular point in time, he's saying that let's start asking qualitative questions like, for instance, is the solar system stable forever, right? Will some planets, if you like, fly off to infinity? So if you're not able to tackle the problem analytically as Newton did, his idea was that, could we say something about a system even though we can't really solve it analytically and have a formula that governs that system? And this idea has permeated this area of dynamical systems for a long time. So you would see that we'll have even a single equation, and the question is, suppose that I can't solve it. I can't solve this and tell you that y is equal to x plus cos x or something. Suppose I can't do that, and the problem is non-linear. Can I still say something about the qualitative behavior of the system without actually solving it analytically? So that was the point of view that Poincaré came out with. And dynamical systems is basically of qualitative explanation of things. Okay. So he developed a very powerful geometric approach to analyzing such questions, this qualitative approach. And it is now one of the main approaches in modern subject of dynamics. And of course, as I mentioned before, this has gone beyond celestial mechanics. Like, I don't even look at the orbits of planets, right? I apply this to different areas. Of course, my area of interest is fluid dynamics, and I'm interested in mathematical biology and biological systems as well. But his ideas have gone beyond celestial mechanics. And he also actually was the first to discuss the possibility of chaos. Chaos is a deterministic system that exhibits, a periodic behavior. In other words, you don't have things moving in circles. But they depend sensitively on the initial conditions, okay, which means that it is very difficult to do long-time predictions. Okay, so he came up with that possibility that it is possible to have, instead of just having this, this planet orbiting circularly or periodically, you can still have a system that is not periodic and has some crazy behavior. So he came up with that possibility. Well, but the equations that govern these kinds of aperiodic systems are nonlinear. Of course, we know that nonlinear problems are difficult to solve. They often don't have analytical solutions, for most practical ones, right? And so the invention of the computer, high speed, in the 1950s, that led to a huge revolution in the study of dynamics. That's in Dynamical Systems. The computer allowed then scientists to be able to experiment with all these nonlinear equations that they couldn't solve before, and to look at combinations of parameters and to see how the system evolves with time, which was difficult before computers, because then you have to compute this by hand and all of that. Okay, so that gave scientists and mathematicians intuition about the behavior of nonlinear systems. Okay, so using computers, Lorentz did a lot of experiments and discovered what is now called this strange attractor. You would often see this symbol here, this thing here in most dynamical systems text and even differential equations referred to as a strange attractor due to the work of Lorentz. Okay, so by studying convection rules in the atmosphere, he gained some understanding of the fact that the weather is really unpredictable. Okay, it's very unpredictable based on the fact that it is a nonlinear and a chaotic system. And he found that solutions never settled. Unlike previously, his solutions, he looked at three solutions. The solutions never settled to equilibrium. They had this, crazy behavior going on. Instead of, nines, continuous oscillations like sines and cosines, his solutions were very chaotic. Okay, and he also found that if he started his simulations from two slightly different initial conditions, you could start with, if you like, for example, 0.1, and then start the same system at 0.11, and yet the results will be totally different from each other. Okay, often you don't want that. We say the system is stable. If I start from 0.1, from 0.11, I don't expect the final results after a long time of integration to be very different from each other. But in a chaotic system, that can happen. And that was what Lorentz was finding in his experiments. Well, the implication of all of that was that the system was inherently unpredictable, right? It's very difficult to predict it, especially he was looking at the weather. And so small errors in your measurements, right, of the current state. So you have the current state of the weather, you make measurements. If you make errors, you could have very embarrassing predictions because the system is chaotic and it's not a linear problem. So he's been quoted as saying that when a butterfly, referring to this unpredictability, when a butterfly flutters its wings in one part of the world, it can eventually cause a hurricane in another, right? Basically trying to make the point that it's very challenging and difficult to predict the weather. Okay, so that was from Newton to Poincaré to Lorentz. They all contributed, and earlier dynamics, or if you like, dynamical systems, was basically used in trying to solve celestial mechanics problems. Okay, but whilst this was going on, and even Lorentz came around to try to apply this to the weather, other developments were going on in dynamics in the 70s. People were looking at fractals as well as mathematical biology. Fractals are basically, you could use these equations, either discrete equations to make these nice plots from a computer, right? These are not like pictures. This is, these are actually made. They are called fractals. I haven't fractals much, but people were making this, and especially Mandelbrot used this. He codified this. He could code them up, and he made them very popular because of these nice pictures that he could get from them. At the same time, you had mass biology being developed, and Winfrey applied this geometric approach, geometric thinking to biological oscillations, especially the heartbeat, right? He applied dynamical systems, which is to this. So that is a way of historical information concerning dynamical systems. But as I said, to do the math, you guys are now mathematicians. You have to have some idea of differential equations, some of the techniques, and then how these are actually applied. Again, some of this information here will be useful later on. If you can consider the application here as basically motivation actually for dynamical systems. Okay.